Good evening. Okay. My plan for this stream is just to try to do some tidying up and some cleanups, bug fixes, that kind of thing. Don't know how long it'll be, but I don't intend, unless I get particularly excited, to try to do any new constraints. I do have a constraint in mind if I get there, though. Right. So, the last time that we worked, we had a problem, which was that Thermo Case 12, which is, as I recall, Frost, was crashing out at this point. And we weren't sure why, because we thought we'd fixed that. I have since then done some thinking. So if we start by turning on... if we start by coming into here and switching over to Frost, that's probably the best starting point, really. And I'm going to grab another terminal. And if we now cargo run, we should get the Frost panic. And the panic basically is that here we end up eliminating the 1 from the base of the Frost thermometer. And the reason is that we're going the row 6 column 3 to row 3 column 3 thermometer, so that's the one straight up, and the row 6 column 3 to row 1 column 1 thermometer, that's the one that went sort of up and sideways, eliminates 1 from row 6 column 3. So the problem basically is that the 1 in row 6 column 3 leaves only 2 as being possible in row 5 column 3, but this is a pair of pairs where the, quote, the non-common, as it were, end is the same thing. So that's basically the problem that we can see, is that the non-overlap cell is also overlapping, and so we're causing a problem from there. So if we come along and we go to the cell pair constraint and we find our double cell pair constraint, then ignoring that joyful clippy problem for now, we're asserting that we get an overlap, and that's good. And if you recall, in the rule, we tried to ensure that when you got the overlap, if they were the same, then it deduplicated, and we did that by switching to a hash set. But then we added a name in, and because the names are different for the two thermometers, that's why the hash set subsequently hasn't done the elimination that we need. So what we're going to look for in the double cell constraint, and in fact we can store it in here, and we can have double overlap. It's just a Boolean. Oh my goodness me. Down here we can say that whichever of the overlaps we have, the double overlap is if cell A is overlap, then we care about oh goodness me, how am I going to render this nicely? If cell A is the overlap, then whichever of... no, I don't like the idea of doing it like this. Let's... Very briefly, let's pop out and grab... the cell pairs rule as well. So here... we've got the overlap and we've got the other from, whichever the other is of A and the other of B. Yeah? So if other A is equal to other B, then it's a double overlap. So let's just pass double overlap in, which we can do by passing in other A equals other B. And let's go over here. Double overlap is a Boolean. And we take double overlap here. And we pass in double overlap there. So we now know if it's a double overlap, and the rule that we had before was that we had to have, at least one member of permitted AB not in permitted CD or vice versa, which gave us this constraint. And this is true if we're not a double overlap. If we're a double overlap, all we need is at least one member of permitted AB to be in permitted CD, which, is subtly different. So if double overlap, we need at least one of permitted AB to be in permitted CD, since that could be the other cell. So permitted AB is a vector of borrow cell values, permitted CD similarly. So what we're interested in is there's got to be at least one. So if permitted AB dot iter dot any given AB value, permitted CD contains AB value, we know there's an overlap and therefore everything is good. So what we can do then is we can say, if not any of that, we're broken. Well, in practice, we need to compute the overlap, because then we can constrain to the overlap. I think that's probably nicer, because so overlap value is the value we're considering in the center cell. So if there isn't a joint, if there isn't a value which exists in AB and in CD, we need to eliminate the overlap value. So we can say see, the eliminate function is going to be the same both ways. So if double overlap and XD double overlap and we're going to go boopy boop. Surround that with parentheses. Did that work? I don't know. Delete the blanks off the end. X D P the other cell. A double overlap case. We need at least one permitted AB to be in permitted CD, so that could be the other cell. Be-doo. And I'm going to be really weird here, and what I'm going to do is I'm going to put the if there, and then what I'm going to do is say paste there, or if not double overlap, there must be at least one member of permitted AB not in permitted CD, or vice versa. And here we can go. So, by whatever means, the overlap cell value cannot stand eliminated. And now the question basically is, how do I... If I put that there, it does a bit of reformatting. And if I put that there, it does much more reformatting. So Rust format does not like it when I put comments in the middle of expressions, which is fair enough. So I reckon that's probably reasonable. Nope. Okay. So one thing that we don't know is whether we actually do have double overlap. Whether we're ending up with that set. So let's just very briefly assert not double overlap, just to see whether or not we hit that. Okay, so we do, which means that we are getting double overlap set in some cases. In the double overlap case, we need at least one of permitted AB. Okay. So we're going to break this down a little bit, and we're going to go... permitted AB. Right, so this is PAB. PCD. And we'll see which values that prints out immediately before it says thermometer blur eliminates one from. Right. So this is this. So this is saying that, you know, permitted AB is the value 2. Permitted CD is the value 2. There's only one way to do that, which means that we end up trying to eliminate that value. But in that context, are we doing double overlap? True. Oh. Thing we've not checked here is not self double overlap, and that's better. There we go. So that's probably the cleanest answer here, which is that if we're doing a double overlap, then there either needs to be at least one value in permitted AB that's in permitted CD. Otherwise, if it's not doubly overlapped, there need to be a pair of values such that one is in permitted AB and one is in permitted CD, so that we can do that, because otherwise we're trying to put the same value into the same, well, the same, not just the same value, but the same cell filling, so the same symbols into two different cells in the same region. Which would be bad, okay? So let's have a look at where we are with that. This is going to be Kaji rules. Add double overlap check to double. So double cell pair relationship needs to know if it's a double overlap, since that has different elimination rules. There we go. Okay. And then we can restore that, because there's no point. Okay. So that was the bug fix that I wanted to do. Let me just go and tick that off in my to-do list. Next, what we want to do is have a look at the cell value type. So what I'm thinking about here is that cell value has a vector of symbols in it, and my concern here is that's more allocations, it's more complicated for comparison. Just generally speaking, it's an unpleasant thing to have sat there. So what I was thinking we could do is we could just add another arbitrary constraint, and our arbitrary constraint here is that we won't have more symbol sets than we can fit into some width of integer, such that we can have a copyable value that represents a collection of symbol IDs. And it's always going to be a complete collection of symbol IDs that's in a cell value. So, you know, we can optimize to some extent there. So what I was thinking was we would design a data type that represented that, add the constraints to the puzzle builder that will mean that we can't violate any assumptions that we make in the implementation of that type, and then we'll convert cell value to use that type. And my ultimate goal would be, at the moment, all of our things that deal with cell values only deal with them if there's a singular symbol set. And I want to make a mechanism to enable us to work with multiple symbol sets at some point in the future. As you know, I've been talking about doublers as another kind of cell symbol set that we want to use. Goodness me, my brain is gone. So let's get on with this. So my gut feeling is that we probably want to do this in symbols.rs. Raw symbol set builder, symbol ID, maybe. Because it's going to kind of be a little bit like this, but actually maybe we don't. So I tell you what, we're going to do it in puzzle. So we're going to design, and we'll derive debug and partial EQ for it. Pub struct. Now what this is this is a complete collection of symbol IDs. So I'm going to call this a symbol collection. And like symbols are, like symbol choices are U32s, which means that there's 31 possible symbols in a symbol set. That can be represented in 5 bits. If we had a U64 here as our symbol collection value, and we could stick like a repr transparent on that to prove that we're never going to have anything more complex than that. So 64 bits, if we put 5-bit values into that, we could fit 12 5-bit values into 60 bits. And that would leave 4 bits. 4 bits can represent numbers between 0 and 15. 15's more than 12. So what I suggest is that we say that 12 symbol sets is the maximum that we can store. And a symbol collection, therefore, can represent between 0 and 12 symbol choices in sequence. But always a complete set. So like it can either be just a symbol from set 0, or it can be a symbol from set 0 and a symbol from set 1, or one from 0, 1 and 2, and so on. So we're going to import symbol collection. And basically, I think that we only ever want to be able to create new ones of these internally. And that's just going to return a 0. We're going to have a push that takes a mute self and a symbol a symbol, which is a symbol ID. And what this is going to do is we're going to assert that the symbol we're trying to push in is the one we're expecting. It is of the set that we're expecting, and then we're going to insert it. Yeah. So what we're going to say is we're going to say symbol into parts. And if you remember, the parts specifically are the set number and the symbol number. We want to assert the equality of the set number and self dot count. We'll go with len, because we can. So fn len, and in fact this can be public, and it's going to return a use size because that's what the polite thing to do for a length is. And we're going to have const length mask, which is a U64, is and we said it was 4 bits, so it's going to be 15, well, OXF 000 000, that's 32 bits. Sorry, that's 32 bits. That's 64 bits. So that's the length mask, and we can do length shift. Which is 60. So len is self.0 and self length mask. Shifted right. Oopsie, length shift. And it's going to complain that that whole lot now needs to be as use size. And symbol collection has a public len method, but no isEmpty method. And well, I'm just going to go self.len is 0, because that's the best way that we can implement that. So we are going to assert that the set number we've been given is the current length. So that means the first symbol that we insert has to be a symbol from set 0. And then what we're going to do is we're going to self.0. Again, I'm just going to go const value mask u64 is 0 fff 1 2 3 4 1 2 3 4 1 2 3 4. So self.0 and self value mask, or sim number as u64 shifted left by 5 times set number. I could probably need to stick parentheses around that. So that's adding in the symbol number. And then we need to OR in again. Self.len +1. And that whole lot shifted left by length shift. And that's going to be self.0 is all of that. Okay. So that whole thing needs to be as u64. Okay. So we can now push values in. The next thing that we want to be able to do is to index into this, because if we know its length, we want to be able to index. And indexing into the symbol collection should produce a symbol ID. So let's write that. So we're going to go impl index for symbol collection. What we are missing is a couple of bits and bobs. So the type of the output is going to be symbol ID. We return a borrow self output. So indexing is always returning a borrow. That's disappointing because we can't do that because we don't actually contain the thing we're going to synthesize it. Okay, never mind. Instead of impl index, we're going to go fn get. And we'll do it this way around. So we're going to assert that an index is less than self.len, i.e., does this symbol actually exist? If it does, then the symbol number is equal to self.0 and self value mask shifted right by 5 times index, and that whole lot and that, which is 5 bits. And we're going to return a symbol ID new from IDX and sim number as usize. And that can be public because you're allowed to request symbols. I'd like to make symbol collection iterable. So we're gonna, another thing that we can do actually is we can derive clone and copy because they should be. And if I import iterator for symbol collection, then item is going to be symbol ID. And the way that this works is going to be if self is empty, none. Else, we want to get the symbol at we want to get the top symbol. So let sim equals self.pop. In fact, we can just go self.pop. So let's just do that. So self.pop. In fact, we can go one further. Let's just say self.pop and let's write pub fn pop, which returns an option symbol ID. And if we're empty, none. Else, what we want to do is say, okay, ret is some self.get self.len -1. And then all we need to do in this middle bit is we need to somehow decrement the length. And we can do that by saying self.0 is self.0 and value mask, or self.len -1 as u64 shifted left length shift. Pop needs to be mutable, so we can stick that. And now we can iterate them as well. And we can say pub fn iter, which takes self and returns an import iterator item equals symbol ID. Just returns a copy of itself. And we can also import into iterator for symbol collection. So the item is symbol ID. The type it returns from this is a symbol collection. And it returns self. Oh, we don't even need to do that, actually. That's covered by a blanket implementation. Lovely. Excellent. So the only thing we can't do directly is index into it. Which is frustrating, but, you know, we can deal with that. Let's add the new constraints to Puzzle Builder. So Puzzle Builder has a push symbol set that takes a raw symbol set and pushes it. And this is where we need to assert that self.symbols.len is less than 12. Because that is our constraint for the number of symbol sets that we can have. I will be one moment. Sorry about that. Needed a little bit of a coughing fit. Okay. So where were we? Yeah. So we've just added the that symbol set limit. That's not a problem. And what we want to do now is we want to change cell value so that instead of having a vec of symbol IDs, it has a symbol collection. So many errors. That's all good. Go to the next diagnostic. It's not G, D. No, it's square bracket D. There we go. So we've been given a vector of symbol IDs when we're creating a cell value. We don't want that. We are going to, again, change that for a symbol collection. And then do that. Here we are returning a borrow symbol ID, a borrow list of symbol ID. We're not going to do that either. What we're going to do here is we're going to return a symbol collection. So again, because bear in mind that these symbol collections are copy. There's no reason we can't just return it. There we go. And now next diagnostic. So our next diagnostic is here where we're computing the cell values. We've got symbols, which is the set of choices that we've made, and we need to turn that into a symbol collection. So we're going to go let mute symbols, or let mute collection equals symbol collection new. I tell you what, actually, let's go one better than that. Let's go all the way back up to here, and let's import from borrow. So from a slice of symbol IDs for symbol collection. Assuming symbols are sorted. Early collection first. So, not early collection, early set first. Let mute ret for sim in value. Ret push star sim. Ret. Go to next diagnostic. So it's not symbols, it's going to be borrow symbols is already a borrow, so it's just going to be symbols dot into. Will that work it out? No, it won't. Of course it won't. Can I do a symbol collection from symbols? No. In that case, I'm going to call that function from slice. And we're going to go all the way back up to here. And we're going to grab that entire function, paste it in here, call it from slice, and save that. Go to diagnostic. Right. So this is just a clippy hint that we had before. But of course, if we open the workspace diagnostic picker, then cell pairs and odd even are now broken because we've made it so that you can't just treat this as a slice of symbol IDs. So all we're going to do now is, I think somewhere did we assert that the symbol count is 1? Values is cell values if you've got, yeah, blah, 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 blah. Yes, so we're asserting that there's only one symbol value. So we can just go let sim0 equals value.symbols. So values 0, symbol, no, xd. Here, we can say sim0 is value.symbols. That's a symbol collection. And we want the 0th entry off it. But for now, there can only be one value. So we can pop it and we can unwrap that because we know for a fact it will be present because here we asserted that the length was 1. So there we go. I mean, this is still bad because when we get to the point of having more than one symbol in the puzzle, we're going to have to recode this, but it's fine for now. Let's find the next error, which will be in cell pair. So here again, we've asserted that value A's symbol length is 1. So we can let sim A be value A symbols pop unwrap because that's fine. And we can change that for sim A. And then here we can change that for sim A. And then here we have the same sort of thing for value B. So sim B is going to be value B symbols pop unwrap. So symbol B. Go to the next diagnostic. So here we have the overlap symbol. So I'm going to let sim O be overlap value symbols pop unwrap. And in fact, I'm going to delete that from there. And I'm going to double check here whether or not we check that there's only one. We don't. So here, what we're going to do is we're going to go assert overlap value dot symbols dot len is 1. So that the moment we hit the first time that this doesn't work, we can fix that. So sim O is the symbol that we're using. And then, yeah. I think I'm going to have to turn off the drop inlay hint because that's just a little bit too noisy. Right, so the picker now is clear, and so my question now is, does that at least still work? It does. Hurrah. And what this is going to open us up to into the future is the ability to look at adding to the board state values that we've eliminated as symbol collections, but that we cannot eliminate as individual choices in the symbol sets because there's still some overlap with values that we want to retain. And that will be a really powerful thing for us to do when it comes to the more complex puzzles. So I'm going to quit out of that. And we're going to probably end up committing all of that in one go. And I'm going to go Kaji rules, add concept of symbol collection in preparation for when we want to eliminate values rather than just symbols from cells. Make sure cell value is simpler by adding a copy type for collections of symbols. Okay, that chore done. Let's just very briefly, doesn't really matter where we start because what I want to do is grab the entire diagnostics. Let's just very quickly clean up some of these clippy lints. So here, replace the closure with region ID itself. Yeah, fair enough. And now here, it's basically complaining that there are too many arguments to this function. And I mean, there are, but I don't really think that I want to change it for now. Later we might, so we're just going to turn clippy too many arguments off for this function. I don't normally like doing that, but in this case I don't really want to change it. In theory we could add a builder, or we could group up like those 4 values and those 4 values, but it's just a mess, so let's not do that. You know, indeed, we could possibly even derive all of the double cell pair constraints by iterating over all of the cell pair constraints, and then we could pass into cell pair relationships and it would futz about with that. But again, I'm not going to worry about that for now. We can tidy that up another time. So there are no more diagnostics. So let's just have a quick check. Sure. Clean up some clippy lints. Okay. How long have we been going for? Well, not too long. Let me refer back to my notes for a moment. So, cell value needs to not have vex symbol ID. I've done that one. Support to board to remove values. So that's the thing I hinted at. I'm not going to do that now. Consider one or more of the following rules. Well, we did clone cells, so I can tick that one off. I'm not going to do vaults for now. Slot machine. So the only possible constraint that we might want to have a go at is region indexing. And let me bring up Firefox window and bring up fpuzzles and show you what I mean by that. So if I go for a 6x6 grid, which is always easier to explain in these kinds of things, then what an indexing cell is it's some cell that you mark. Let's, for a moment, you know, say it was that cell, right? And what we say is we say that in this cell, whatever digit is in here, so what symbol is in here, or, you know, in later cases, maybe the value in this cell, and let's say that's a 4, for argument's sake. Oh, I'm going to change the highlight to a darker color. Let's change it to that. Let's change it to that. Right. So that 4 there, what that is telling us is that typically speaking, let's say this is a column indexer. So what it's saying then is it's saying that in this row, column 4 contains a 3 because this is column 3. So then that would imply a 3 there. I don't know why highlight came in, but never mind. And you could do the same thing if you said that this was an indexer in the column instead of an indexer in the row. Then the presence of that 4 there would say that within this column, the 4 that puts a 3 there. Or it can be a box indexer, in which case it's saying that within this box, then that 4 goes 1, 2, 3, 4 goes there. Sorry, 3 goes there. Typically, you only get row or column indexers. So let's delete that highlight for a moment. And fpuzzles can do those. So if we come over here, you can see that there's row indexer, which it says if cell RC has value V, then cell VC has value R. So if row 1 column 1 has a 4, then row 4 column 1 has a 1. So that's the indexer in that direction. It seems a bit odd that that's called row indexing, but it's because what it's saying is the index of the row is what matters. And then column indexer is if RC has V, then RV has C. And it mentions this is the one used by the 159 constraint. If we pop very briefly back to a 9x9 grid, and we imagine all of column 1, all of column 5, and all of column 9 being column indexers, so 1, 5, and 9 all being column indexers, then this is a standard kind of Sudoku called 159 Sudoku because of the indexing of the columns. I have a simple 6x6 called 1 to 6 that uses row and column indexing. So what we could do is we could input that, show how it solves, and then maybe have a go at writing an indexer constraint, which might be fun. So let's do that. So let's pop the given digits in first because they're nice and easy for me. So those are the given digits in our puzzle. And if I asked just, with no extra constraints, there's at least 100 solutions to this puzzle. And if we ran the solution path, it really doesn't get very far. It manages 2 hidden singles before it gets stuck. So let's go ahead and add row indexers. Remember, row indexers say if RC is V, VC is R. So within the column, the row number is what's being indexed. And so I reckon I need to set all of those and all of those to row indexing. Then I believe I set all of those and all of those to column indexing. And if I'm right, that solves. And it does. And it's pretty simple. There's one mention of a contradiction here, which might trip us up implementing this. But you never know. We might be able to do it via another fashion that doesn't require contradictions. So let's enter this. This is called 1 to 6 inclusive by me. Don't know whether we can do cosmetic cell coloring in fpuzzles. Don't think we can. I don't recall whether the highlights are carried over. If they are, then in 1 to 6 inclusive, those cells were coloured blue. Those cells were coloured pink, which I'm assuming that is. Those cells were coloured white, which I can't do, so I'm just going to assume that's the default. And then down here we had, actually that's not pink, that's red, isn't it? By whatever value we're going to go with. And then we had red, orange. Well, that's more pink. I'm going to say those are pink. So we're going to go red, yellow, light green, dark green, blue. That'll do. Anyway, that's the rough shape of that puzzle. So let's solve it. Let's save the solution and clear it. And then let's produce the JSON. And we can see here that we get row indexer and column indexer as new things. And we also get cage. Cage is just the cosmetics, like we got lines before. So we're going to have to add that to our fpuzzles loader. And row indexer, every entry just has a collection of cells. And column indexer, every entry just has a collection of cells. So what we're going to do now is we're going to try and implement those into Kaji. So let's grab the JSON and copy it. And I will just fling that over to my other display so that if I need it back, I can get it back. So this is called 126. There we go. Kaji bin source main. I want you to load 126. And the first thing that obviously will happen is that we're not actually going to be able to load because we don't know about row indexes, column indexes, etc. So Kaji loader fpuzzles. We're looking for a thing that just has cells, but not necessarily values. Clones has cells and maybe clone cells. Fpuzzles XV pair has cells and maybe a value that's a string. Fpuzzles ortho pair has cells and maybe a value that's an option I32. Guess what we're going to have? We're going to have an fpuzzle cells data type. That just has cells. That's a vector of fpuzzles cell ref. So, row indexer. Column indexer. And cage, which we know to be cosmetic data. So that loads, finds those two hidden singles, and then fails to solve. Okay. Next stage, we need to teach the puzzle data about indexes. So this is a piece of data. So pub indexes should be a vector of usize, usize, and then indexer kind. Sudoku grid rule indexer kind. So Sudoku grid rule pair relations has a cell pair relationship. I'm just going to call it a Sudoku indexer kind, and we're going to grab that out when we get that. So now let's go along and pull up. It's an indexer, a constraint. An indexer is a constraint. Create indexer. And we're going to pub use indexer. And of course it's going to complain that it can't do that, but that's okay. Just make note new and write that as Kaji rules source constraint. No, it's not a new one. What am I doing? Indexer RS. Indexer cells. And for now, we're just going to go pub enum Sudoku indexer kind. And that has row, column, and box. And those are the indexer kinds. And we need to XYP. And we want to grab that as well. There is no indexer. Now there is. Okay. So we can come back to here and we can import that. And it's going to complain that Sudoku indexer kind doesn't implement debug. That's easy enough to do. Like that. There are no more diagnostics, so we've now added indexer to there. So now we need to add it to the fpuzzles constraint. So we're going to explore from here to the converter. Here we go. So for row indexer in val.row indexer. For each cell in this indexer, we're going to add it as a row indexer, because each cell can be considered individually to be a row indexer. Okay. For cell in row indexer dot cells. Actually no. Yes. Grid rules mute. Indexers push. Cell.row, cell.column. Sudoku indexer kind row. Y P call indexer call indexer call indexer column. So we've converted all of them into stuff that goes into puzzle data now. Pardon me. So now all we have to do is determine and create the constraint types, and then we can implement the constraint. Okay. Buffer close, buffer close, buffer close. Let's just verify that it runs and fails in the same way. That's correct. Rules Sudoku. So we've implemented all the cell pairs. Now add all the indexes. For row, column, kind, in, raw, rules, indexes, iter, copied. And now it's going to complain that it can't do that, and that's fine. Let's come back to here, which is where we need to be, and let's derive clone and copy, because it's a trivial constraint. Unnecessary use of copied. Okay. I mean, let's assume that we don't need to do that. What happens without that? We get borrows everywhere. Ugh. I mean, maybe, you know, we can shut that up by sticking a borrow there. Yeah, okay. So we now have row, column, and kind available to us. And what we want to do is we want to construct an indexer for that and add that to our builder. So let's pop across briefly to our into here. Let's derive debug, because we have to for this. And so let's have the cell, which will be a cell index, and the kind, which will be a Sudoku indexer kind. And actually, we don't even need the kind here. We just need the region that we're indexing into. So region ID. Impl indexer new. And new takes a cell and a region. And that becomes a self. Now, we're actually going to have to go a little bit cleverer than this, because we're also going to have to take a symbol set that we're going to read symbols out of. So set, which will be a symbol set ID. And then cell, region, and set come out of that. Now it's going to complain things are never read, but that's fine. And now we can import constraint for indexer. And our missing members. How difficult is a constraint to implement? I mean, it's about the same as a cell pair. Not that hard, but not that easy. So let's go difficulty easy, but maybe plus 1,000. And there's nothing to do to prep the board, really. Because, well, there isn't. Replace qualified path with use. Okay, we will have something to do in the logical solve, but we don't need to do that in order to implement the next bit. So let cell be rows r-1, c-1, and region be match kind. Sudoku index a kind row. So in here, the region that we care about for this cell is the row that it is. So let me get this right. If it is a row indexer, then it is indicating the position of the corresponding row number in that column, which means that it's the column we need. So if we're doing a row indexer, it's the column is the region that we are indexing into, because we're finding the nth entry in the column, which is a row. So let's just remind ourselves of where our column regions and row regions were created. So we've got region rows, we've got cols, which I'm going to rename to region cols. And we've got box cells, which is the cells, and then there's boxes, which are the regions. So I'm going to rename boxes to be region boxes. So we've got region rows, region cols, and region boxes. And then we just need to find where all those get used. And here you see we are converting them. So we don't want to convert them. What we want to do is we want to iterate them so that we can retain the values for later use. And then we can just go like that. So we haven't broken anything yet. And then down here, we can complete what we need to do. So if it's a row, we want region cols, the column that we are in. If we are doing column, then we want region rows, the row we're in, because we're indexing the column in the row. And if it's box, then we are indexing the cell within the box, and that's the one where it matches. So it's region boxes. And we need to know the box for this cell. So that might be a little bit cleverer. So to do, work out the way to find a box. But since at the moment we haven't syntax error, expected semicolon, there's your semicolon, expected semicolon, found close brace. Right, okay. At the moment we're not generating index a kind box, so we don't really need that, but I want to leave the to do in there to remind us. So we've now got the cell and we've got the region it belongs in. We know the symbol set because that's the digits, so we can do builder add constraint indexer new cell region and self.digits. So that adds the constraints in. Now it's still going to just do nothing, which is exactly what we expect. So now we need to think about the logic for an indexer. So what is the logical step involved in an indexer? Well, basically similar to a cell pair relationship, except that we're going to do a lot of scanning within the region. What we want to do, and let me go and grab our setting tool again. So if we think about this top row for a moment, right? The top rows are column indexers, which means that this 2 here indicates the position of the corresponding column number in that row. So that 2 says there is a 2 in column 2 because we're in column 2. That 3 is there's a 3 in column 3. That 1 there says, because we're in column 5, that in 1, so over here, there will be a 5. So that, oh, for goodness sake. So then that 5 and 1 are indexing one another. And then these 2 here are going to be constrained. I mean, they're constrained by the row to being 4 and 6. And you can see that either that's 4 and that's 6 and they self-reference, or that's 6 and that's 4 and they cross-reference. So what I'm imagining basically for what we need to do is we need to say for each one, so we're considering this cell. What values can this cell have? Well, it can't be 1, 2, 3, so it must be 4, 5, and 6. Yeah? For it to be 4, the 4th cell must contain a 1, where it can't, so we can drop the 4 out. The 5 is a 1, so it can be, so we can leave the 5. The 6 can't be a 1, so we can drop that out, and then we would say that's therefore a naked single 5. The other way around of thinking about it, let's consider this 3 for a moment. The fact that this can only be a 3 means that none of the cells other than the 3rd cell can be a 1. So the 3 there knocks a 1 out of all of those, even though obviously the 1s have been knocked out of that. It knocks a 1 out of there. So those are the 2 ways round that we can look at indexing. So basically we can say if we are set, we can do eliminations from elsewhere. And if we are not set, then we can eliminate from ourselves anything where other cells within the region could not be us. And that, therefore, hopefully, will solve everything that we need. I hope that made sense. If it didn't, then I apologize, but hopefully it will as we start to code it. So, 2 things that we can do. One, if we are solved already, then we can eliminate our index in the region from anything but the cell we reference. 2, if we are not solved already, then we can eliminate any value from us which cannot be our index. Any value from us whose cell cannot be us. This cannot be our index. It's all a bit value-y, squiffy weirdness, but that's okay. So, step 1, are we solved? If state dot choices in this cell, no. Yeah, choices, self.cell, self.set, dot solved. So if we have solved our digit, is that fair? No, because we want to do this by values. So we're going to go let our values equals state.cell values self.cell.collect as a vector. If our values.len is 1, So we are solved. There's only one value we can be. And so what we can do now is we can point at every cell that isn't us and eliminate our index as a value from that cell. Yeah. Okay. So we need to know our index as well. So let our region be state.region self.region dot two cells. And our index is our region dot find iter find position. Unwrap 0. Okay. I mean, theoretically, we don't have to compute that now, but, you know, we've got that. So, we are solved, which means we want to eliminate our value from anything else. Rank's saying that he implemented indexing using only weak links. That doesn't help because multiple symbol sets means that we could end up with multiple different combinations of symbols that end up with the same value. And I want to allow for indexes to be, for example, mutated by doublers. I don't know realistically if that's necessary, but I think it's fun to try. And so that's what I'm going for. So our values len is 1 means that we want. So yeah, so we're eliminating our index. I'm actually gonna stick a +1 there just because we actually want because we're eliminating. Are we eliminating symbols? Might be nice to have a generic weak link that works symbolically like that then. Yeah, but also the thing about weak links is that they silently provide deductions, where the goal here is to explain every step where possible. So I'm really only using weak links for what I consider to be blindingly obvious eliminations, like there is a 1 in the row, therefore there can't be another 1 in the row. I'm trying to avoid weak links otherwise. I hope that makes sense. Where was I? Right. Do I want that +1? I'm going to get rid of it again for now, just because it might turn out to be unwanted. Can I associate a step string with each weak link? Maybe, but I've gone down this route now, so this is the route I'm sticking with. I quite like having the logic explained out, not least of which then if I come back later and go, ooh, actually that's not right in that way, I can adjust the logic. And it worked quite nicely for cell pairs and double cell pairs. So that's where I'm going to go with. However, since I have you in chat, how hard would it be to add to fpuzzles slow thermometers? I'll leave that with you. Right, so for other cell in our region, it's copied filter C is not ourselves. Other values is collect a vector of other values. So Not hard to add slow thermos. Oh, fantastic. I'm just being constantly jittered. Let me remind myself again. I'm just going to bring the solver back. So the case we're dealing with here is that 3. And what we want to do in that 3 case is that those are 1, 4, 5, 6. And that 3 essentially is saying that everything that isn't that cell should have a 1 eliminated from it. Like that, which then leaves that as a hidden 1. So let's bring this back. So what we're actually going to go is we're going to go cell index other cell index other cell in our region iter copied enumerate. So our goal is just if OCI does not equal our index. Actually, it doesn't really matter because even if we hit ourselves, the elimination is clean. So what we're going to do is we're going to say other values is state cell values other cell. And our goal is to say that any other value that is not our index plus 1 can be kept. Any other value that is our index plus 1 has to be eliminated. So what we're going to do is we're going to say let elim values is filter v dot value is equal to our index plus 1. And as I32. There we go. Right. So we're going to eliminate values yeah. So that means that, let's say we're dealing with, we are the 4th value in the region. And so we would eliminate an undoubled 4 or a doubled 2. From any cell that is not the cell that we are referencing. So we need to just go if OCI is equal to our values 0.value minus 1. And we'll just stick OCI as I32. Continue. Oh, goodness me. I really need to get better at my editor. This is the cell we are referencing. So skip eliminations. So we have some eliminations that we'd like to try and do. At the moment, we can't guarantee that we can perform the eliminations unless there's only one symbol set for reasons of that which we've discussed earlier. So we're just going to assert, well, first of all, we're going to go if elim values is empty, nothing to do for this cell. Continue. Otherwise, there's eliminations to be done. So what we're going to do is we're going to assert equal elim values 0 dot symbols dot len 1. We only work with single symbol sets, and we'll deal with that again some other time. Action is a logical step action. Indexer. Should we take a name? Take a kind. I'm just going to go indexer at rc. Well, indexer at blah, where that blah is state.cell info self.cell. Pushstra eliminates right, let mute eliminated equals false for elim in elim values. So we're going to try and eliminate this cell value from the cell. If state.eliminate this is other cell, and the symbol, we're going to go sim e, and we're going to go sim e is elim dot symbols dot pop dot unwrap, because there will only be one symbol. Well, I say that's sim c, that should be sim e. So if attempting to eliminate that symbol from the board caused a change, then action dot push symbols from push cells and in fact I'm prepared to stop it there. Why not? We don't need to do more than a single elimination. Return action. So if we manage to do an elimination, we'll return it there. Otherwise, we're going to go round and round and round and round and round. Else, instead of eliminating from elsewhere, we eliminate from ourselves based on the possible values we can be, or we might be able to be. So this is the other way round. This is, and again, let me go and grab the puzzle. So this is where we're going to look at this cell here, and this cell at the moment could be 1, 4, 5, 6. And what we're going to do is we're going to say to it, is it possible that this is 1? And to do that, we would look at that cell and we would go, can that be a 2? No, it can't. Therefore, that can't be a 1. Is it possible this could be a 4? Well, can that be a 2? Yes, it can. So that could be a 4. Is it possible that it can be a 5? Can that be a 2? No. Can that be a 2? No. So that would then eliminate that down to just a 4. And then it would be a naked, and so it would go in, and life would be good. My brain is running out faster than my code. Okay. For my value, for value in our values. Let other cell equal our region square brackets value dot value -1. As usize. Let v equal, well, if value dot value less than 1 or value dot value greater than our region dot len, continue. Well, no, actually we can eliminate this one. Else, now's the question is, can we eliminate based on the values that other cell can be? So in fact, if we say let can eliminate equals true, else it's going to complain, yes, the value dot value as usize. If and else have incompatible types, because this doesn't have a thingy yet. So we found the other cell, and the question is, can the other cell be a value that represents us at all? So wanted value is our index as, oh, it's already as an I32, so we want -1. No, +1. And now we want to say other, so state cell values, other cell, any v dot value equals wanted value, and we do the elimination if not. So if that other cell cannot possibly be us, then we want to eliminate. If can eliminate, then let's try to. Action is logical step action indexer at push stra self eliminates format self cell, yeah, self eliminate, and again we're going to assert equality on value.symbols.len, and 1 can only operate on single symbol sets. Self, so push symbols, state dot symbol. Let sim e is value dot symbols pop unwrap. If state dot eliminate self dot cell sim e dot changed return action. I mean, let's just see how badly that goes. No, it solves. Yay! So what do we get? We get some hidden singles. We get indexer at row 2. Let's actually try to follow this through. What I'm going to do is I'm going to pull the puzzle over here. And I'm just going to take that solve list over to my other screen temporarily so that I can follow through the sequence. So it says hidden single 2 at row 2, column 6. Sorry, hidden single 2 at row 2, column 6. So that 2 eliminates 2s from there. That 2 eliminates 2 from there. That 2 eliminates 2 from there. That is a hidden single 2. 2. Let's go into solving mode to do that. So 2. Hidden single 1 at row 6, column 4. Row 6, column 4, it says, is a hidden single 1. And that's in column 4. And the right way to choose that is it says that 1 eliminates from there, that 1 eliminates from there, that 2 is full, so that leaves that as being the only place a 1 can go. Indexer at row 2, column 1. Row 2, column 1. Self eliminates 5. And the reason it achieves that is because that cannot be a 1. Indexer at row 2, column 1. Self eliminates 1. Why can that not be a 1? We got that 2, we got that 1. And that's going down there. Why can that not be a 1? Indexer at row 2, column 1, self-eliminates 1. That doesn't sound right, but it did solve. So self-eliminate means that it didn't find anything that had our wanted value. So here I'm just going to go println we want to be wanted value. It's going to be a big mess of text on my other screen for a moment. Indexer at row 2, column 1, self-eliminates 1 because we want to be 2. Ah, I'm an idiot. We don't actually need to increment wanted value. Word. It's not our value. Sorry. It's our index plus 1. So undo, undo. Yeah, our index plus 1. Wanted value. Did we already add 1 to our index? No. So how is our index 1 at this point? Oh my god. Because I am an utter idiot. It's an indexer, but it's of course the other way around. Let's go again. I wonder if anyone spotted that. No, no one said anything. Excellent. Right, so clear that, go into solving mode and carry on. So hidden single 2, row 2, column 6. Row 2, column 6, hidden single 2. Hidden single 1, row 6, column 4 in column 4. Indexer at row 2, column 1 eliminates 5. And it eliminates 5 because this cell here, this 3, can't be a 1. And it eliminates 1 because that can't be a 2. Hidden single 1 at row 3, column 1 in column 1. So we now know that can't be a 1. We 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 know that can't be a 1. That's the only thing that can be a 1 in this column. Indexer at row 2, column 2 eliminates 6 because that can't be a 2. It eliminates 5. That can't be a 2. It eliminates 4. That can't be a 2. It's already got 3 eliminated. And it's already got 2 eliminated, so that leaves it as a naked single 1. Row 5, column 3 here is now a hidden single 1 because we've got 1, 1, 1. Indexer at row 2, column 3 self-eliminates 5 now because of that 1. So that 1, yep, that makes sense. Hidden single 5 at row 1, column 1 in box 1. The only place now for a 5 in box 1 is there because it can't be there because of that 3, and it can't be there because of that 1. So that one is 5. Hidden single, pointing cells in row 1. Row 1, column 4. And row 1, column 6, remove 4 and 6 from there. That's fair. Indexer at row 2, column 4, self-eliminates 3, which leaves that as a naked 5. We now have a naked 3 at row 2, column 5. We have a hidden single 3 at row 6, column 6. The indexer at row 4, column 3, 1, 2, 3, 4, column 3, yeah, self-eliminates 5, because that can't be a 3. It self-eliminates 6, because that can't be a 3. And yeah, it just keeps going in that fashion, one by one, little deductions. It's definitely good. It's not, you know, the prettiest description, but it's definitely good. It definitely works. That makes me very happy. Okay. Let's go ahead and add the test case. So this is going to be case indexer 1, 2, 6. And we're good. Cargo Clippy is just telling us that we never actually use the set in the indexer, which is correct because we're operating entirely on values. So let's go ahead and delete the set. Which means that we can come back to here and we can get rid of that argument, which means that we're now not using symbol set ID here. And we're clean. Good. Right, so git add Kaji rules add indexer, cell indexer, constraint Kaji loader, add fpuzzles support for indexers. Add 1, 2, 6 indexer example. Ensure we test it. Right. So we've added indexer constraints. I can tick that off my list. And I think that means that next time we really do want to do an eliminate values mechanism so that we can basically pass symbol collections into the board to eliminate, and we can have the board consolidate that so that it can then do the eliminations from the symbol sets as appropriate. Okay, I think that's all I'm going to do for today. Thank you very much for watching. Ranks, thank you for your comments, and if you do add slow thermos to fpuzzles, please do ping me and let me know so I can update my my Tamper monkeys. Good evening, everyone.